That's impressive. I don't think I've ever filled out a room before. So I'm sure you all are here not for me specifically, but because you're more curious about Square, which is good. So it's about time. Let's go ahead and get started. Because we have a lot of material to cover, so I will try to speak quickly. I just had some espresso before I got started. Normally I speak pretty slowly, like this is my normal speaking pace, but I'm going to try and ramp it up a little bit. But I could actually probably talk for hours, but I have to cram everything into 50 minutes. So first, a quick blurb about Square. If you live in the United States, you've probably come across Square. You probably already know about it. If you live outside the United States or outside of one of these countries where Square officially operates, then maybe you haven't heard of it, and I highly suggest you go to square.com and check out what they do. In one sentence, you could say we are an honest financial network for everyone. So we do money things, take payments, peer-to-peer, all that kind of stuff. Financial network, lots of financial services. We operate globally, primarily the United States, Canada, UK, Japan, Australia. And we store a whole bunch of payment transaction data in MySQL, which is why I'm giving this talk. And naturally, we are hiring. So not just San Francisco is our headquarters. There's actually offices everywhere. So really, I highly encourage you to check out square.com careers. Great company, love working for them. So let's start off, first of all, with the numbers, because I know in talks like this, people love to see the numbers to get a ballpark idea of what kind of scale we're working with here. Of course, as typically it is with companies, I can't give exact numbers. For some reason, legal really doesn't like that, or comms, I don't know why. But I did run these slides through legal and comms, so they approved it. This gives you a ballpark idea of what we're working with at the moment with Square. As everything, things keep growing, et cetera. Over 4,000 unique MySQL instances. We run Percona Server 5.6 with row-based replication and GTID, not fully yet, but we're getting there. Internally, we have a 99.95% SLA, and we almost always beat that by far. And if you can't calculate that off the top of your head, because I certainly can't, that's 43 seconds a day, 5 minutes a week, et cetera. So a pretty good internal production SLA. Like I said, we usually beat it. We're dealing with about 1 petabyte of data in total, just in MySQL. We have about 800 physical servers, just for MySQL. And this isn't a talk about, physical versus, going in the cloud and stuff. But we do primarily run our own hardware and our own servers. And right now, it's taken about 800 physical servers just for MySQL. And all that powers roughly in the ballpark of 300 microservices, which internally we call apps. So that gives you a rough idea of the scale we're working at. It's not Facebook scale, but it's definitely large enough to be a lot of fun and to keep us up at night sometime. So I wanted a theme for this talk, and the theme is pebbles, not boulders. So what I mean by that, and we'll keep revisiting this theme throughout the talk, is pebbles are like working with a lot of smaller databases, like they're shown on the left, versus one gigantic database. And when it comes to doing MySQL at scale, especially this scale, and I'm sure even beyond this scale, it is so much easier to work with a lot of little databases than it is to try and do something with that gigantic boulder and rock. So, if at your current company you find yourselves with these analogous boulders, these huge databases, especially if they're like databases shared among multiple applications, you've probably already run into the fact that it's really difficult to work with this big thing because it's so important and it's difficult to move or do anything with it. But it's a lot easier to work with little pebbles, little databases that are smaller in size and you can move around and stuff. So again, this is a theme for the talk, and you'll see how we implement it, and we'll keep coming back to this theme. So, topics. A lot to talk about. Quickly, we're going to first go over the basic setup and replication of a production cluster to kind of lay the groundwork. And then I'll talk about how we use that basic production cluster to achieve high availability inside Square. Then we're going to talk about how we do backups. Then we're going to talk about access and security, which as a financial services company, you can imagine is very near and dear to our hearts. Then we're going to talk about monitoring alerting. And finally, because like I said earlier, I could probably talk for hours, but I don't have hours to talk, a list of various advices when it comes to running MySQL at scale. So let's get started with basic setup and replication. This is one standard production MySQL cluster for us. There's a lot of different ways that you can set up MySQL replication, a lot of different ways that you can define a production cluster. We have chosen this, and it's very simple by design. In the next slide, I'll go over the highlights and benefits. But let me just point out what you're looking at here. So again, this is one standard production MySQL cluster. And in it, we have 4 MySQL instances that we call nodes. And so they're numbered here, nodes 1, 2, 3, and 4. We have 2 nodes in one data center and 2 nodes in another data center, the top and bottom segments there. So one data center is typically on the US West Coast, and another data center is typically on the US East Coast. And we run out of just one of those data centers at a time. It's active. And that's what the red node means. So the red node is the active node. It's taking all reads and all writes. In the arrows represent replication. So O1 is replicating down to O3 in a different geographically separated data center. O2 is replicating down to O4, again in a different data center. And then O1 and O2 are a master-master pair, but we don't do dual writes. So only one node is active and writable at a time. So this just makes it easier to flip over, that I'll talk about in the next segment. So the other division there is the A side, B side, you can see. This is largely for a kind of conceptual division in our minds. Because only one node is active, that also means that one side is also inactive. So in this picture, it's the B side is inactive. And again, I'll talk about why we do this and how this helps us achieve high availability and stuff. So again, this is one standard production MySQL cluster, 4 nodes. That O1 node currently is active, it's writable, and it takes all reads. Very simple. 2 data centers, 2 sides. So let's look at some of the benefits of this. The first benefit, of course, is that it works. And it works at this scale. Obviously, if it didn't work, we wouldn't use it. And it's simple, and that's, again, kind of the point. As I mentioned earlier, there's a lot of different things you can do with replication, with MySQL. You could use, Percona ExtraDB cluster, Clara cluster. You could use, SQL proxy, HA proxy. There's all these kind of solutions you can do to achieve both scale and high availability and stuff. You could do dual writes, if you have a master-master setup. But we went for the simplest setup with the fewest moving parts. Because it's also a balance of cost, redundancy, and complexity, especially since we are running our own hardware, and again, we're a financial services company, we're very sensitive to the cost of things. But you can't be so cheap that you sacrifice redundancy. And on the other hand, you can't be so complex that it becomes operationally difficult to work with. So in this kind of 4-node production cluster, it turns out to be a really good balance between cost, redundancy, and complexity. I mean, obviously, you'd get a lot more redundancy if we had a 3rd data center or like a C side and all these extra replicas. Sure, you get a lot of redundancy, right? But now you're increasing your cost, you're increasing your complexity. So it's always kind of a trade-off and a balance between these 3 things. And I can tell you that, running this, at scale, it's a good balance and it works. It scales pretty well all the way up to the numbers we've been talking about. As I mentioned, this doesn't preclude adding like other read replicas if you really want to do that. It doesn't preclude other kind of setups, but we simply don't do it because we want to keep it simple and balance cost, redundancy, and complexity. So as I mentioned before, that inactive side, what's it good for? Well, it's good for a lot of things. It's where all the fun happens because you don't want to touch the active side. Definitely don't touch the active side. So the inactive side is good for doing backups, maintenance, upgrades, and patch. We also let humans do ad hoc queries on the inactive side because, again, like we treat that active node as very special and privileged. It's the thing taking, production reads and write. You don't want human beings, going in there and, potentially causing a log jam with ad hoc, long-running queries and stuff. But they need to do this anyway, so let them do it on the inactive side. And also, the real fun bit is that the inactive side has no SLA. It's essentially kind of off the map because it's not active. And so we don't have to worry about the SLA, which is really important because if you're going to do stuff like maintenance or patching MySQL, I mean, how are you going to do that while maintaining the SLA? So the inactive side, this A side, B side concept is simple but really powerful because you can use the inactive side to do all these things that you need to do, but you obviously can't do on the active node. So, and the last one is, and we'll talk more about this in later slides, is this kind of simple setup where we don't give applications all these extra read replicas and stuff, and we don't give them these huge database clusters, these boulders, forces us and forces the apps to think about sharding and scaling out from the very beginning. Because if an app says, oh, just give us this $1 million hardware and this huge database and stuff, we're going to say, no, that's not how we do things. We need to have a different discussion around sharding and scaling out. Because at this scale, you absolutely have to shard and scale out. I say absolutely. I suppose you could try and buy gigantic hardware and accomplish it, but probably not advisable. So again, we come back to this theme, pebbles, not boulders. So for us at Square, the pebble is this seemingly simple 4-node production cluster, but it allows a lot of flexibility, very powerful, it scales very well. It's not some gigantic boulder that we struggle to work with. So, second, high availability. How do we use this standard production cluster to achieve high availability? So first, let me tell you about our RWC name and our RW SIP. So first of all, the SIP is really just a VIP, a virtual IP, which is really just a floating IP address that you can move from one node or one machine to another. So it's just an IP address you can take down here, put up there, move it around really easily. We have an RWC name, an actual DNS entity, which always points to that RW SIP. And it's the RWC name that the application uses to connect to this cluster. So the application is always connecting to that RWC name. Why is that important? Well, because sometimes when we want to do maintenance on this O1 node, it's active, right? So we need to make it inactive. What do? We flip the SIP. That's what we call it. So we just move that RW SIP to the O2 node, to the B side, and that RWC name's following it. And so the application will notice this because it was previously connected to the O1 node, and we just killed that node and moved the SIP over to the O2 node. Internally, we call this a success over, which has anyone not, is anyone there? I see at least one other Square in here. Has anyone outside of Square ever heard of a success over? You have? Really? Interesting. I wonder if it originated there. He said he heard about it back at YouTube. Interesting. We'll have to ask our colleagues about that. So in any case, the more normal industry standard term for this is a failover, which we'll talk about here in the next slides. We call this a success over because nothing was failed, right? There was no problem. Our previous situation was this. Everything's fine. We just want to move the active node to the other side so that we can do maintenance on the A side. So we don't want to, give people anxiety that there's a failover in progress. No, we call it a success over, and all we're doing is moving that SIP. So we move the SIP, we make that O1 node read-only, we kill connections on the O1 node, and well-behaved applications follow that RW SIP pretty well, pretty quickly. In fact, sometimes the flip can take, as quick as 500 milliseconds. The application just sees MySQL to connection errors for 500 milliseconds to maybe a second. And then voila, you're on the B side, and now we can do stuff on the A side. So we do a lot of these because obviously you have to do maintenance on your clusters on both sides. So going back to the true failover concept, what happens when, let's say we're, like in this picture, we're active on the O2 node, and then that O2 node blows up and goes away, it dies. This happens, especially at scale, this starts to happen more and more frequently. If you have one server, you might get good continuous operation of that server nonstop for years on end. But when you have 800 some odd physical servers like we do, and over 4,000 MySQL instances like we do, things fail every week. Sometimes there's weeks where maybe things don't fail. It's not on a day-to-day basis yet, but it's definitely, failures become constant. They become a way of life. So in this case, like I said, the O2 node was active on the B side, but then it dies. So what do? Essentially the same process. We move that RW SIP back over to the A side, and because something was actually failed in this case, then we call it a failover. And everything moves over to the A side, and as the picture shows here, we simply rebuild the O2 and the O4 nodes, usually like clone them from a backup. We can also clone them, for example, maybe from that O3 node. But you restore the nodes that have gone missing, you set replication back up, and then you're back to a normal cluster. So it's really just this dance of moving the SIP around. Speaking of failovers, a worse situation, so in this picture, we're back to being active on the, let's call it the US West data center on the top portion, and we're active on that O1 node. But what happens if a whole data center dies, which is far less common than individual nodes dying, but data centers do die for various strange reasons sometimes. So in this case, if that data center at the top, like the US West Coast died, as depicted here, then we would do a failover to our other data center. So again, we would move that RW SIP down to the O3 node in this case. We could have moved it to the O4 node. And if this cluster is running GTID, then we can wire up the replication on that O4 node to the O3 node using auto positioning. If this was not a GTID cluster, then it would be a little bit more difficult to wire up replication. We might be down to one node. But in any case, it's just a failover. We're still up and running. And we quickly, as possible, reclone that O1 and O2 node there up at the top. Again, we can clone them from backups, or we can clone them perhaps from that O4 node. One way or another, we restore those nodes. We hook replication back up. In this case, we're still in the other data center. We're running from the bottom. But if we wanted to go back to our US West data center, we just, again, it's always the same dance with this SIP, just moving that SIP around. We move the SIP back up to the US West data center, that O1 node, flip replication around, and then once again, we're back to a standard production cluster. So this is really the kind of like heart and backbone of our high availability. This simple 4-node cluster and this RW SIP that's dancing around the various 4 nodes. Sometimes we move it over for normal operations. We call that a success over, because as most of us know, you always have to do these kind of operations, upgrades and whatnot. So it's easy to move that SIP around. And the other time we move it around is when things fail. Hopefully just, like the O4 node fails. If that fails, then it's super easy. It's, inactive side, inactive data center. So just reclone it from O2, no problem. But if something that was active fails, just move the RW SIP off it and life goes on. Rebuild the failed stuff, hook up replication, and you're good to go. So that is the gist of our high availability, how we achieve that 99.9%, 99.95% SLA. But what about scaling out? Again, this theme of pebbles, not boulders. So let's say that we have an application that's currently running with one cluster, and they want to scale out or scale out reads or writes or something. We don't say, oh, we're going to give you bigger hardware or something like that. We say, we're going to give you a lot more clusters. And this is a very simple way of scaling out. And all these clusters are the same, so it doesn't necessarily increase our complexity any. We basically just somewhat force it upon the application to choose on their side how are they going to shard and use multiple clusters. So it's a lot easier, when you have one cluster, they just have one thing to connect to, all their data is located there. But the bigger apps have many clusters. And then, apps choose various sharding mechanisms to distribute their data across however many clusters they need, and they do it that way. This works pretty well because, again, from our side, it's just one more cluster, right? And it's nothing special. An application can have 1, they can have 10, they can have 100 of these clusters. It's really relatively all the same for us. And it works pretty well for the apps too, because once their application is coded such that it is designed to reach out to many clusters, then again, we just add another cluster as they need it or remove clusters if they don't need it. And this helps scale out both the size but also the read-write workload. So this is a lot better solution, in my opinion, than trying to scale out with bigger hardware. We could take these singular clusters and increase the hardware, use faster storage or something like that. But that's that cost consideration. It's not very cost efficient to do that. And then you have mixes of hardware and stuff. So we try to offer this commodity MySQL cluster to all the various apps. And then we just say, hey, however many of these things you need that we can actually have the hardware to support, we just keep scaling out like this. So again, this goes back to this theme, pebbles, not boulders. Our pebbles are just tons and tons of these standard clusters all over the place, and applications choose how they want to shard and distribute their data across them. So, backups, everyone's super fun favorite topic, but pretty important. So, in a word, Percona Extra Backup. Not very surprising, right? Who's here is using Percona Extra Backup? See, maybe I should just take this whole section out. I mean, I guess if you're not using it, you probably look into it. Percona Extra Backup's been around for quite a while. It's pretty much the standard go-to for MySQL hot online non-blocking backups. And there's a simple reason for that. It works really damn well. We use it on all of our production and go into a few more points about it. Like that second point there says, to be honest, our backup approach is a little heavy-handed. There's it's heavy-handed in the sense that we take full daily backups in all of production every day, which is, again, kind of heavy-handed. A more nuanced backup approach would be maybe like you take a full backup one day and then do like, deltas or differentials over the rest of the week or something like that. But again, simplicity is a virtue, right? So there's nothing more simple than back it all up every single night, which is what we do on every inactive node in every cluster across production. And of course, we encrypt them. We also monitor it. I put this point in there because one thing that seems somewhat, say, not common to me is, does anyone here want to admit to not backing up their production data? No? So that means everyone is backing up their production data? That's good. Is everyone monitoring that? Does anyone want to admit that they're not monitoring their backups? No? Oh, well, awesome. See, why am I up here talking? You all have got this already. That's awesome. Yeah, well, in any case, well, maybe someone will watch this online later and they'll be like, yeah, monitor your backups. What an idea. Yeah, it's important, so we do monitor all our backups. So if there's a single cluster in production that the backups didn't run for some reason, we know about it. We get paged, like we will get a PagerDuty page on it. So that's really important. Like, what's the point of taking backups if you're not sure that they actually completed? So of course we monitor our backups. Another kind of somewhat heavy-handed thing we do with our backups is we actually store them locally. Separate RAID arrays, separate drives, but it's on the actual physical server. Some of them we ship up to the cloud and stuff, but by and large, we store them locally. That does help, again, when we're restoring nodes. If a node dies and we want to reclone it from a backup, et cetera, that helps because the backup's right there. So we don't always have to do like a full something. But, it works if you got the hardware for it. Our backup is relatively simple. It's really just a Ruby script around calls to extra backup and to do the monitoring stuff, and I'm going to show that here on the next slide. I'm not saying this is like something you can necessarily reproduce, but it'll give you an idea of how we run it. And then last point, as I've mentioned several times before, we do verify that we can actually restore our backups because we do this all the time. We use them to rebuild nodes and stuff. So speaking of that somewhat simple Ruby script, obviously I'm not going to show the whole script because that makes a very terrible, terrible slide. But I wanted to give you just an idea, and don't worry about writing this down. In fact, one of my colleagues told me there's actually some option in here that's not correct. This wouldn't work. I wanted to give you just a basic idea of what it looks like to run all the various things that we do for backup. And I'm going to upload the slides so you can get this offline and then study it later. But there's a lot of things going on here, and I'll step through it piece by piece. So the first big part, of course, is the call to inno backup X. And again, I'm not saying like use these particular options, it's just giving you an idea of how we do it to achieve various things. Nothing too fancy here. You know, the important one is probably the stream, XB stream. So we're streaming the backups out. Mostly so then we can start piping it into other stuff. So we're taking the backup, we're streaming it out, then we compress it with PIG-Z. Then we encrypt it with GPG2. Then we run it through T so that out one side of T we can get an MD5 checksum on the final backup product. And then out the other side of T, we're running it through split. So we don't have one massive backup file. The backup file is split into roughly like 2 or 4 gig chunks. So it's really not just as simple as like, oh, just call extra backup, right? If you want to do all these things, you know, run extra backup, and compress it, and encrypt it, and checksum it, and split it. It takes a relatively gnarly command line thing like this. So, you know, again, we're going to upload these slides, you know, point of reference. You can maybe adapt it to your particular needs. So that gets us about halfway through the presentation. This is just a funny slide offered with no explanation, just to refocus everyone's attention. So, 4, access and security. As you can imagine, every cluster is application specific. And what I mean by that is, let's say that we have this application called foo, and foo has 2 clusters, and let's call them foo001 and foo002. There is a kind of logical and very strong boundary around those foo things. There could be another cluster for application bar shown there on the right, like bar001, and it might sit like right beside the foo clusters on the same physical machine, but foo can only access its own clusters. We don't have applications share databases or anything like that. So in the world of foo, it only sees its foo stuff there in the blue bounded box, and all the other stuff is very logically separated. Foo couldn't even connect to bar even if it tried. There's no user privileges or user accounts or anything like that for it to even connect there. So obviously, you know, this level of isolation. Is anyone here doing shared databases, multiple applications, one shared database, if they want to admit to it? Yeah, a few people. I mean, I've heard that before. It's not totally uncommon, right? But this is one of our access and security things because, you know, with security, the whole kind of theme there is about reducing the attack surface, right? So even if someone compromised foo, they only get foo data and no data for any other applications. So TLS for all connections and all authentication, no passwords. And when I mean all connections, I mean all connections. We run TLS, which is essentially SSL. It's the predecessor at SSL. Even if it's not going outside the same switch, even if it's staying inside the same cabinet, everything is TLS. There is not any unencrypted traffic on our network. Again, financial services company, so you know, to be crazy about security. So TLS is good for all the connections because there's no ability to sniff the network, not even locally. And what I mean in terms of authentication is you can't crack a password if there's no password. So with MySQL, you can actually use TLS certs as authentication, which is what we do. So this is just an example, and you can look it up in the MySQL manual later. This is a pretty probably high-end requirement because it essentially means that you're running your own certificate authority inside your company, which then, you know, someone has to set up and maintain and keep very, very secure, because if your certificate authority was ever compromised, that's more than the keys to the kingdom. That's like in the Matrix, getting access to the key maker himself. So, but nonetheless, it has this benefit, which is there's no passwords, right? So it's all these TLS certs. And those are what applications use to authenticate with the database. So no passwords are stored anywhere. We also, of course, so there's kind of 2 points in this point. The first is that we have kind of logical separations. We have accounts for human beings, we have accounts for the application, and then we have accounts for system stuff like a backup user. I don't think this is too surprising to most people. The point here is you should, partition these things because they have different access levels, different controls around them, et cetera. So we don't just like lump all, MySQL accounts into, MySQL accounts. Humans versus apps versus systems, we keep separate. And then the more important point is that we rotate these constantly. So they don't stick around forever. It's much more difficult to hit a moving target. And again, all these use TLS certs, and so those certs are rotating too. So everything is in kind of constant motion. Granted, this is a pretty high requirement because it takes a lot of tooling and automation to be constantly like changing these certificates and these users, but this is the section about security, right? So that's about as good as it gets, keeping them rotated. The other part is isolated security zones, which limit, well, let me just show you the picture here. So let's say that we have 2 security zones, and for simplicity, we'll just call them the blue zone and the red zone. And we have a standard production cluster in the blue zone and one in the red zone. First of all, these zones are completely separated. There's no access or anything between them whatsoever. From one zone to the other, they essentially don't exist. The blue zone that's in its world, it's the only thing that exists. The other thing about these zones is that only inbound TCP port 3306 is allowed, which of course is the MySQL port. So very strict connection into this zone. You can only have incoming TCP 3306 ports connections, so obviously you can reach MySQL. By contrast, everything outbound is blocked. So not only are the zones very isolated, no kind of crosstalk or anything, they're very difficult to get into, and you can't even get out if somehow you plopped your self down in the red zone and we're trying to get out. It's not possible, it's blocked. So this eliminates, that's what I mean by directional there in the point, it's directional. It's only inbound traffic, not outbound traffic. No crosstalk, they're completely separated. And we also do no hardware reuse. So if we wanted to take hardware from the blue zone to the red zone, can't do that. Hardware never leaves the zone. So very, very isolated stuff, very like bulkheads in a ship, right? Again, all about reducing that attack surface. So if someone somehow got into the blue zone, not only are they limited to that blue zone, but they would have gotten into one specific app, and as we talked about in the very first bullet point, they're limited to that app. So, I mean, I'm no security expert, but it's difficult to imagine how you can reduce that attack surface even more. And the last one, nothing to show about this, just a general mention. Especially with us as a financial services company, we're legally required to do these kind of things too, but auditing, paper trails, et cetera. Everything we do, everything a human does, there is some sort of record outside of the database, usually far, far outside of the database. A record of who did it, when they did it, why they did it, what they accessed, et cetera. So if you really want to up your security game, you can think about implementing some sort of auditing and paper trails, et cetera. Again, pretty high requirement. Could be tedious sometimes, but security, right? So, monitoring and alerting. Probably no surprise, the bottom one, PagerDuty. Is anyone not using PagerDuty? Oh, a few, that's cool. Yeah, PagerDuty, pretty common. SignalFX, probably less common. I think it's relatively new. To be honest, I don't know. It's a hosted metrics. And it works out pretty well. This isn't a talk or a promo about SignalFX, but if you've never heard about them, I know, go check them out. Square uses them. We send all of our metrics up to SignalFX, and they take care of all that for us because the point of this being is unless you are SignalFX or unless you are like Datadog or Vivid Cortex or something like that, this is probably not your business, right? It's definitely not Square's business. We're not in the business of doing metrics and monitoring. Is there anyone here from like Datadog or Vivid Cortex where this is your business? Oh, okay. Well, then never mind. You have to do this all yourself. But that is your business, so that works out for you. But my advice is, if you can, outsource that. Like, find a company like SignalFX or someone and just ship your metrics up to them and let them do it and save yourself the headache. So we do that. And we do it at scale. and it works. And again, I don't work in the finance department, but usually the more and more scale, you can kind of negotiate a better deal. So if you don't like the price they're telling you, just tell them you're going to grow 10x in the next year and get a better contract deal or something. Local and remote monitoring. So we do monitoring both on the actual MySQL node. So not very surprising, right? Probably all of us have some sort of monitoring solution running right there beside MySQL that connects to MySQL, does show status, et cetera, and then pulls those metrics out, does performance schema or something. So that's not very uncommon. You need that, of course, but you also need, in my opinion, as we do, you need a remote monitoring solution. And the purpose for the remote monitoring, so this is monitoring running on completely different, microservices application. And what it's doing is it's looking at the cluster from kind of a high-level top-down view. And it's monitoring for things like, does the cluster have only one writable active node? Which is super important, because if you remember going back to the original slides, I said that a production cluster only has one active node, one writable node. If there's ever 2 or more writable nodes in a cluster, that is a very, very bad day. I mean, that could be a potential split brain situation. That is bad news. It's that kind of like top-down monitoring that you can't really do easily if all you have is local monitoring, because the monitoring on the O1 node only sees O1, and the monitoring on O2 only sees O2, and the same on O3 and O4. You need remote monitoring to look at the cluster as a whole and say, is the cluster configured correctly? Does, weird things like, does the RWC name, when you access that, does that actually get you to the writable node? So these kind of top-down monitoring things. So both local and remote monitoring. Query metrics. So this is like Vivid Cortex is a good example of this. PMM also does this. Essentially, this means take the queries out of the slow log or the performance schema and ship them up somewhere, do something with them. So in Square, because PMM and Vivid Cortex don't quite work for us, and because this is my background and what I do, tooling and MySQL stuff, we wrote our own custom in-house query metrics thing that parses the slow log and sends it up to a centralized application so all the app owners can access their query metrics. So the important point here is that you do this. Obviously the standard metrics, threads running, QPS, things like that are important, and I'm sure we all monitor for that already. That's why I don't have a very boring list of like, take these metrics out of MySQL. Because that's, I think, pretty well known and also written in about every MySQL book that's been written. The greater point is that the query metrics, again, out of the slow log or the performance schema, are invaluable, mostly to the application owners. As the DBAs, we don't go poking around these because I don't know what the applications are doing, and frankly, I don't care. But it's super important to them. So find some sort of solution. If you don't have any right now, at least start with PMM. It's free, open source. Percona, actively develops it. Give it a try. Look at solutions. I think Datadog does this. New Relic has some MySQL monitoring and stuff where it'll pull up queries, Vivid Cortex, et cetera. Very important for the application owners. So the next kind of 3 slides, the next 3 points are all kind of related. Interestingly enough, I was just having a conversation with some colleagues last night at the open reception about this. So at Square, we only page and alert the DBAs, people like me, for basic stuff around whether the MySQL instances and the cluster and the backups are alive and correct. Very basic stuff. Stuff like replication lag, ooh, I'm running on battery power. That's weird. Okie dokie. So stuff like replication lag goes to the application owners. Thanks. And like I said, I was having a conversation with some colleagues last night where they're DBAs at their company and they get paid for replication lag. But what can the DBA do about replication lag if you're not the application owner that's using that database? All you can really do is contact the application owner and say, hey, what are you doing? We've noticed this replication lag. And so, in effect, the DBA becomes this, powerless middleman. So instead of waking up one person in the middle of the night, now you're waking up a first person who wakes up a second person. So maybe this is somewhat controversial, but my advice would be, if you're a database administrator who's getting paged for things like replication lag, like QPS, these things that you really can't do anything about, you know that they kind of indicate like MySQL is suffering or whatnot, but you also know it's the application owners or users of that cluster. My advice would be, and you want to change this at your company, you can say, well, Square does this, and it's working great for them at scale. And it's true. It really does work well. So I don't ever get paged for replication lag. I don't ever get paged for QPS. I don't even get paged for threads running. I only get paged for things, again, like, is MySQL itself alive? Because obviously, if MySQL crashes, that's my responsibility. Is the cluster configured correctly? Again, my example, like, if there's 2 writable nodes, that is a bad situation, and that's my problem. Are the SIPs in the right place and things like that? Because those are the things that I have both the power and the responsibility to do something about. And as the database team, we are assuring that MySQL itself, the cluster, is running and correct. So we're giving the app owners a rope, and they can either do something productive with the rope or hang themselves by it. Sometimes they hang themselves by it. And so those pages go to them, and it actually does work out. What happens is these app owners, they get paged for things like replication lag, and because they're the ones driving the replication lag, they immediately know, oh, it's that backfill that we started 3 hours ago. That's the cause. And then it's great. It works. So again, if you're not doing this at your company, it does work, it does scale, and I think it makes people happier insofar as they can be happy getting paged. So we have about 10 minutes or so left, which is good because we're coming right down to the last of it. So various points of advice here is kind of the kitchen sink part of the presentation. All this other stuff I could talk about but don't have time. So kind of 2 sections. The first is the kind of bad news advice, or the don't do this, or the kind of warnings or whatnot. So the first is everything will fail, which is so true. The larger and larger the scale, the more weird things fail in weird ways. And that's talked about, I think, relatively often enough in conferences and stuff. But what I really mean to bring up by this point is that if you know everything is going to fail, then it's critical, especially at scale, that you engineer for failure, that you engineer for dealing with these failure scenarios, because they're going to happen. And it's not just going to be MySQL that fails. Everything fails. The hardware fails, the hard drive fails, MySQL fails, the network fails, monitoring fails, the firewall fails. Every single thing fails. And I'm not saying try and boil the ocean and account for everything that could possibly fail, but engineer for failure. I think the natural tendency is to engineer for something that works, a working good solution in this pristine world, which obviously you have to do. Things have to work, right? But there also has to be this mindset of engineering for failure, especially at scale, because everything will fail. Manual processes are the killer. I think we all know this already, but it becomes more and more painful at scale because those failures become so frequent, then your manual processes become frequent, things fail in the middle of the night. Manual processes amplify human error, which is a part of life. So everywhere you can, try to root out these manual processes and automate them somehow. It helps scale and helps reduce human error, et cetera. Fancy replication. Again, this is a matter of opinion and style, and maybe there's justification and reasons for more complex replication setups, far more complex than we have. Maybe there's good justification for dual writes on a master-master setup. There's all these other technologies around replication that you can use. If you have a good justifiable use case, then sure, go for it. But our tendency is to stick to simpler stuff. So I shy away from fancy replication. Quick note on the theme again, avoid fleet-wide operations. we seem to do this anyway. We think in our mind like, oh, we have to patch all of MySQL, and we have thousands of them. And it's difficult for any one human to wrap their mind around that. And it just, again, amplifies human error. So try to avoid fleet-wide operations. We try to focus on the cluster as the unit of work, because it's a lot easier to wrap your mind around one cluster and the life cycle of that cluster. And then we just automate and do that 1,000 times for however many clusters. So again, avoid those boulders. Don't go it alone. This is not a, no one pays me to be up here and speak, but if you need to either hire some sort of database MySQL expert in-house and have them on staff. If your company isn't of the size to do that or unwilling to do that, then hire a company like Percona or Pythian and contract with one of their support services. I think this is really important because MySQL is a relatively complicated thing. It's easy to get set up and going, but to do it correctly and reliably, there's so many knobs to turn, and I'm sure you've read the MySQL manual. It's just mind-blowing at this point, the relative complexity of it. So don't go it alone. Hire a MySQL expert or hire someone who's going to become your MySQL expert, or get a support contract with a company like Percona or Pythian. They're really affordable, and then you get access to their expertise. We just talked about this, which is don't alert the poor DBAs on app-specific stuff like replication lag and QPS. It just doesn't work out. Also, don't blindly trust new versions. You would think if you're just upgrading MySQL from 5.6.34 to 5.6.36, just 2 minor level patches, right? It won't cause any problems. Most of the time it doesn't. But again, going back up to that first point, everything fails. We have run into this before. We have all these microservices, and one out of those roughly 300 has some weird performance regression on a patch level update. So it happens. So don't blindly trust it. It could someday come back to bite you. And please, don't use MySQL as a queue or a cache. I'm glad you all laughed at that. So the good stuff, to end on positive notes, test your HA solutions in production. I know it's a little odd to say test something in production, but it happens so often that people think, oh, I've got this high availability solution, especially if it's something like a data center failover, and they think it's going to work, and then their only test is when it's already on fire, and they're like, oh, let's test it now, and they find out it doesn't actually work. As a financial services company, we're actually legally required to demonstrate that we can run out of a different data center. Apparently, this is some legal requirement. So every single application in Square does this. They test that they can run from the East Coast if they primarily run out of the West Coast. And I can tell you, every single time we do it, one application thinks that they're sure that, oh, there's not going to be problems. There's going to be no problems when we switch to the East Coast, and fun things happen. So yeah, test it in production when things aren't on fire. It's going to cause a little bit of a hiccup, but it's better a controlled hiccup than when your house is already on fire. So please test it. Shard from the beginning. If you think that you're going to reach a certain scale, as one of my colleagues gave me a bit of feedback on this point, do some capacity planning. If you think that you're not going to grow beyond 500 gigs total data size, then maybe you don't need to shard. But if there's a real possibility that you're going to be up into the terabytes or petabytes, shard early, like build that in, don't wait. Relatedly is limit your shard sizes. So we try to keep each of those clusters, we try to keep them to 500 gigs each, which sounds pretty small. Why would you only have a 500 gigs of data in each individual cluster? Well, first of all, remember, we can just create more clusters. As it turns out, we have many clusters that are way over 500 gigs, some are in the terabytes. It's not because of the storage size or because terabytes frighten us. It's for reasons like transfer rates. So in small parentheses there, 1 terabyte at 1 gigabit a second with a 90% efficiency transfer takes 2.5 hours just to transfer the data. So if you're rebuilding a 1 terabyte node or something, and you have to transfer it from somewhere, it's 2.5 hours that you're down, that node is offline, reduced redundancy, just to transfer the thing, not to mention like if you have to decompress it or decrypt it. So the size is really about the speed of movement. How quickly can we restore these nodes, move the data? It's not because we can't handle like, 10 terabytes. So limit those shard sizes. Closely related is to have small clusters. Going back to the theme, it's a lot easier to move pebbles than it is to move this gigantic boulder. So keep those clusters small. And then when you automate everything, this is the kind of keystone of it all. If they're small and easy to move around, and then you have automation, then it becomes this fluid motion of moving things rather than straining to try to move that gigantic boulder. We again talked about this as kind of the reciprocal of the previous slide. Monitor for MySQL being up and correct, et cetera, and page the DBAs on that if you can. Don't page the DBAs on like replication lag. Just monitor, is MySQL available as we said it would be. Again, always do query metrics. This is a real saver for applications. Do you use a solution like PMM? Take a look at Vivid Cortex, New Relic. It's super important. And the final one, went by past it, PT table checksum. This tool has had an amazing lifespan. I've given talks about it in the past. We run this inside a Square on all of our production data. We do it several times a year. And what it does is it essentially just makes sure that all your replicas are identical to the current active node, the current master. And I can tell you, every single time we do this, we always find an application or two that has a little bit of drift on the replicas. The replicas have a little bit of data. It's just a part of life. This tool, works great. We run it on the entire production fleet. So if you're not already running it, it's very important that you do. So again, going back to the theme, pebbles, not boulder. Think small, think simple, think small clusters. Make it easy to move around and work with these things and a lot of them, and then just automate your processes. It's a lot easier than trying to do something with that gigantic boulder. So thank you.